I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video where we are looking here at a coordinate geometry application of partial derivatives. Before we look right here at the question, let's look right here. A useful advantage of partial derivatives is that they give you slopes of traces. Keep in mind when you're thinking about basic calculus, the derivative is giving you your instantaneous rate of change, the slope of a tangent line. Similarly, a partial derivative is giving you a slope of a specific tangent. And we're looking here at slopes of traces. What are these? These are traces of surfaces which are curves that represent intersection of a plane and a surface. But everything here is always tangential. You have to keep that in mind. I'll be showing you here as we work back and forth between the computer and this question. I will show you what all of this represents in terms of graphs. What is our question? We have to find the slopes of relevant curves which are cut from a surface of a specific representation, which is this. They have the x and the y and the z axis coming into play. Z is equal to 2x squared plus 3y squared minus 4. We have to determine the slopes of curves which are coming from here by means of cuts. Various planes are coming into play through the point 1, 1, 1, which you know to be x, y, and z. X is equal to 1, y is equal to 1, z is equal to 1, and parallel to your relevant coordinate planes. It seems like there's a lot going on over here, but I'll talk about it before we start doing this question. Keep in mind, partial derivatives are giving you slopes of traces. These will be tangent to that point of intersection where the plane and the surface is coming into play. You'll have a specific tangent you can draw, and the slope of that tangent will be determined from a partial derivative calculation. Look right here at the question. We have to find slopes of curves which are cut from a surface. This right here is our surface. I will show you the graph momentarily. By planes through point P, a specific point. It has an x and y and a z value because it is really this x, y, and a z. That's what it is, 1, 1, and 1. And parallel to relevant coordinate planes. We are looking here at two planes. What are these planes? We're going to be looking at x equals 1 plane and a y equals 1. And these will be parallel to your relevant coordinate planes. What does that mean? Let me show you. You are looking here at a representation which is x, y, and a z axis. And this is how I'm showing it to you. Your z, your x, y, you can take these behind the board and all of that, but I'm showing you only in one perspective. This is what you have. If you are looking here at x equals 1, I'm looking here at x equals 1, and I were to draw a plane which is going through it. If I can draw it properly, and hopefully my drawing is relatively decent, this is my x equals 1 plane. This x equals 1 plane is parallel to a coordinate plane. What is it? Look right here at this point right here. It's your origin. It's parallel to your plane y, origin z. Your x equals 1 plane is parallel to your coordinate plane, which is y, o, z, origin z. Why is it called a coordinate plane? Because it represents coordinate axis and it's going through the origin. Keep in mind again, your x equals 1 plane is parallel to your y, origin z plane. So that's one plane we will be evaluating. What's another plane? Look right here again at your representation. This is what I have. I have a y-axis, a z-axis, and I have an x-axis. Now look at y equals 1. That's my other plane, and it is going to be parallel to another coordinate axis plane. If I have y equals 1 right here, and I draw a plane which is coming through it, hopefully I can do a decent job in my graph. It looks something like this. Then my x, origin z, will be parallel to that. This plane will be parallel to that, and you have to keep that in mind. My x equals 1 was parallel to y, origin z, coordinate plane. You see coordinate plane. My y equals 1 plane is going to be parallel to your x, origin z plane. These are two things we have to keep in mind because they come right here in the question. Let's look here at the question again. We have to find the slopes of the curves. What are these curves which will come about? We will look at that. They will come about from the cutting of these x equals 1, y equals 1 planes of this specific graph. And they'll be going through point 1, 1, 1 and parallel to your coordinate planes, and I've shown you that. Now let's switch over to our computer and let's look at a graph of all of this. So let's log in over here at Desmos 3-dimensional graphing tool. I have no affiliation with it. I'm using it only for this video. And let's plug in our function. We have z is equal to, and I'm typing it for you, 2x squared plus 3y squared minus 4. And we've developed what looks like a paraboloid. X, y, and z axis, you can see it x-axis, y-axis, and the z-axis, and then it's hollow on the inside. So it's not a true paraboloid, but has a parabola style of image and perspective to it, and this is what we have. Now let's start adding some planes. and I'm gonna type them over here. This is us just getting an idea of what we're looking at. X is equal to 1. I'll extend it to 3 dimensionals. We have a plane. X equals 1. Now let's do y is equal to 1. We'll extend it to a dimension. We have y equals 1. And last, let's do z is equal to 1. Z is equal to 1. And this is what we have. Now let's shift over here. You know, when you're looking at the original representation, when you're looking at the very base of this parabola, it's shifted down 4 units. It's kind of covered from all of these planes, but that's why you have a -4 in the graph. 2x squared plus 3y squared minus 4. And when you look over here at the intersection of all of these 3 planes, shifted to the x-axis by 1 unit, shifted to the y-axis by 1 unit, and shifted up on the z-axis by 1 unit, you look right over here. This intersection right here, I'm looking right here, of the green, the gray, the red, and the purple, that represents the point 1, 1, 1. So you can easily zoom in here on your own computer, and this is what we would have. I'm just playing around with it, but this intersection of these 4 colors will give you that point 1, 1, 1. This is where we are going to make the cuts and determine the tangent of 2 planes. What are my planes? X equals 1 and y equals 1. Keep in mind, when I'm looking over here, I'm going to cross out some of these items just for a perspective. This is what I have. My z is equal to 2x squared plus 3y squared minus 4, a parabola-like graph on an x, y, and a z plane, shifted down 4 units. And we're going to make cuts at point 1, 1, 1, but I'm looking at only 2 planes, x equals 1 and y equals 1. Let's shift over now to the board. So this is what we have. X equals 1 is parallel to our coordinate plane, y, origin z, and y is equal to 1 is parallel to x, origin z. How do we start? Consider this. When I'm looking at the first plane, x is equal to 1. I'm looking here at my function, z is equal to 2x squared plus 3y squared minus 4. If I know x is equal to 1, I can plug it right over here. I have z is equal to 2 plus 3y squared minus 4. When I clean it out, I have 3y squared minus 2. Z is equal to this. This represents one curve. Find slopes of curves. This right here is one curve. We have it here. I'm going to just put it over here because I'm going to show you graphs of all of these so you have better perspective. Your one curve is z is equal to 3y squared minus 2. This is when x was equal to 1. Anyhow, now if you do the partial derivative of this, you can determine the slope of the tangent line at that particular point, 1, 1, 1. And you'll do partial derivative with respect to z and y because the x variable has been fixed, the y variable is being differentiated. What do you have? When you're looking at this 3y squared minus 2, it's easy. The derivative here is a 6y. If I'm telling you, look over here, x, y, and z, x is equal to 1, y is equal to 1, z is equal to 1, you do here y is equal to 1, and you know the slope over here of that tangent at that particular point will be equal to 6, and it will be right. That's your one answer, because we have to find the slopes. As you know, we have to find the slopes of curves. The slope of this particular curve, z is equal to 3y squared minus 2, at this particular point will have a value of 6, the tangential slope value of 6. Let's look here at the next curve where y is equal to 1. When y is equal to 1, you know we're looking at a plane parallel to x origin z. You're doing z is equal to, you put y value of 1 over here, you'll have 2x squared plus 3 minus 4, and then it is equal to 2x squared minus 1. Here's my next curve, z is equal to 2x squared minus 1. In this curve right here, you're seeing the x variable has gone. In this curve, you're seeing the y variable has gone, which is fine. Now you'll do the partial derivative here with respect to the x variable. The derivative of 2x squared minus 1 with respect to x is what? It'll be 4x. Look right here, 1, 1, 1, x is equal to 1. Your slope here will be equal to a 4. The tangent slope over there is equal to 4 at that particular point, 1, 1. How can we verbalize these answers? When we're looking at the plane x is equal to 1 and we're looking at this particular graph over here, and we know that plane is parallel to this specific coordinate plane, we are developing a curve, and that curve is z is equal to 3y squared minus 2. At this particular point, the tangent will be a value of slope 6. When we're looking at the y equals 1 plane, which is parallel to this coordinate plane, and we make a cut with regards to this using the y equals 1 plane, we are developing a curve whose function value is z is equal to 2x squared minus 1. At the point 1, 1, there's a specific slope. The value of that tangent slope is equal to 4. Both of our answers, 6 and 4, should be correct. Now let's switch over to our graph. We can represent all of this for you. When x was equal to 1, we had a specific curve develop, and that curve was 3y squared minus 2. That's what it looks like. This is me rotating it around and you're seeing it. This is 3y squared minus 2 is equal to z. But we said x was equal to 1. Let's put in x is equal to 1 and let's give it an effect. This is what we have. And then let's bring in our other value, z is equal to 1, because that's our centering value, z is equal to 1. And you can look right over here at this particular junction here of the green, the blue and the purple. We have a particular point. At that point, what is the slope of that tangent you can draw? Well, the slope was 6. And I'm going to change the contour appearance here so you can see it exactly in a linear manner. And this is what you're seeing. You see right here. If you were to draw a tangent line to this parabola at this particular point right here, which is the junction of these three colors, blue, green, and purple, you develop a tangent line slope to be equal to 6. Now, this was our first set of items we developed. Now, let's look at the other ones. This was here with regards to the x equals 1 plane. Now, let's bring in our second set of curves. When y was equal to 1, we developed a curve, a contour curve. What was that? Z was equal to 2x squared minus 1. And it's developing. Let's add here our y equals 1 plane, and we will give it a three-dimensional effect. I'll show you this momentarily. And let's bring in our anchoring z is equal to 1 plane. This is what I have. Now let's switch over here to this view. Look at all of these colors. I have green, which is my z is equal to 2x squared minus 1, my parabola-like curve. Then I have the y equals 1, my purple, and then I have my z plane, z is equal to 1. You're looking here at the junction of green, purple, and gray. At this particular point, if you were to draw a tangent, what would the slope be of that tangent? I'm going to change the perspective so it's easier to read it. You're looking here at the junction of green and gray and purple. And when you do that, you're seeing here, you were to draw a tangent line over here. The slope of that tangent line would be a specific number, and that would be 4. We've determined it already, and it would be correct. So this is what we're talking about. Partial derivatives are coming into play to determine these slopes of your traces. What we do now as we close it out is switch back to the board. When you have these type of questions, you're looking for slopes of your traces, which are cut from a specific surface equation that you have, and you're using planes to make cuts at a particular point. The derivative of that particular point is determined using partial derivatives, and we use two planes. These were planes parallel to your coordinate planes. One of ours was x equals 1 plane, one was y equals 1. These are actually lines, but when you give them a dimensional effect, they become planes. X equals 1 plane, y equals 1 plane, because this is going through the point 1, 0, 0 on an x, y, and z axis. This right here will be going through 0, 1, 0 on an x, y, and z. That's what my planes are. What I did at the end, always bringing in that anchor z equals 1, was I was always centering around over here, because the intersection is actually 1 unit across on the x, 1 unit across on the y, but 1 unit above on the z, which is why you always have to demonstrate that. So you can see the accurate intersection point from where the tangent was developed and where it was demonstrated. One curve was z is equal to 3y squared minus 2, the other one was z is equal to 2x squared minus 1. Here the slope was equal to 6, here the slope was equal to 4, and both of these answers will be correct. Thank you for watching.